Thank you, Tegwin. So the next talk is coming from WellID. We've spoken a bit about acoustic images and we've spoken a bit about EM, electromagnetic images. We're now going to hear about a new technology from WellID, which sort of combines both of them together. So please, with that, I'd like to hand over to WellID and please give us your talk. Thank you.
Thank you. My name is Lars. I'm CEO in WellID. I've got Roland Chemali that's also been following this or working with this, the data I'll show you here today. And what we'll present today is a new LWD tool using pulse echo radar to do imaging. So both caliper and microelectrical imaging. So first, we'll go through the operating principle of the radar. And in difference from traditional resistivity tool, this is a pulse echo. So the wave physics has similarities to what you would find in a pulse echo acoustic tool. We send out a wave and we record the waveform when it's received. And from that, we use the time of flight to as caliper, and the amplitude and the reflected signal is then processed into image showing microelectrical properties. This is the LWD tool. It has 4 antennas. We started with building it for a big boreholes, 12.25, 16-inch, 17.5-inch. And the reason why we started with big boreholes was that that's the area where acoustic tools have most challenges. The LWD acoustic tools gets heavily attenuated by the mud weight and the big boreholes. We have 4 sensors, 90 degrees apart, and when you rotate, you get a full image. Use approximately 150 pulses per second with 4 sensors. And the tool, it's always preferred to be perfectly centralized, but it's not as critical as with some other sensor physics or with acoustic tools. What we get reflection from is the electrical impedance difference, the contrast between the drilling fluid and the formation. So if you have exactly same properties in the drilling fluid and the formation, we will not get a reflection. And you might have seen this if you take a glass into pure oil, the glass will disappear because the properties are the same. So we rely on a contrast to get a reflection back. You can also say if you get very little signal back, that also gives you information. So even though you don't get the signal back, that can be all very interesting information. The impedance is related to the resistivity and the permittivity of the formation, and same with the oil-based mud. And all this is frequency dependent. So we operate at center frequency of 3.8 gigahertz. So when we do characteristics of the mud, we do that in a wide range of frequencies. So this is a typical properties. So when before a job, we would look at mud composition, and we would also do a test with the VNA, so characterize the mud as a function of frequency and also function of temperature in many cases. So we understand we have the measured value there, and then we also have the modeled value. And OBM is at lower frequency, it has some different properties than at the gigahertz range. So it is important to consider the frequency here. This is an example on how we have modeled OBM versus frequency in terms of conductivity and permittivity. And then you can add on temperature here in addition. And it was interesting what talked about earlier from Baroid about the oil-based mud. So it has to be an isolator for us to send a signal through. The radar get attenuated if it is conductive. So we need an isolator or a high resistivity mud to be able to send the signal through. This is some more from a publication about different mud properties. And the mud property is one thing. The mud cake, as Roland mentioned, is another part that we see is the next that would be really interesting to characterize to get further to true resistivity when we from electrical properties or an relative measurement to get closer and closer to true resistivity. But in general, many of the publications are at lower frequency ranges, up to 1 gigahertz, and obviously because that's been the most common frequencies to operate in. So when we do test with mud, we go all the way up to 20 gigahertz, and just to have it for later on. The operating principle is that you have you receive an echo, and the standoff will be have a function on the time. Those are related, and also the amplitude due to geometric spread of the wave. And all this is then simulated, and we use that when we are taking it from a received pulse into electrical properties or resistivity. And then you can have different permittivity, you can have different standoff, different resistivity in the mud, and all this is modeled. The range that we are typically looking at have been in 12.25 to 17.5 inch. We have been measuring boreholes up to 22 inches in the field. That's the biggest borehole we have measured, but it was not that signal stopped. It was still possible to measure bigger boreholes. We are likely going to go down in sizes, but that's the tool we have at the moment. Then yeah, some more modeling, and we use those modeling again to get to the resistivity. So some examples. So if you're drilling in the dark, you need to turn on the light. So this is an example from a 12.25. We see here multiple spirals. We see spirals that are 90 centimeters. That's bit to first stabilization point on the RSS. And then we see another one that was 7 to 9 meters in the tangent. It came in the tangent. And all these spirals creates challenges when you are going to do microelectrical imaging. You have a different standoff. You need to compensate for that. And also the attenuation is continuously different. And then you have ledges, you have other effects. So that's the downhole environment that we work with. Here you see in a more traditional way of visualizing. It shows a caliper image where the light color is then a high standoff. And we can see it comes 180 degrees apart. This was a vertical well. And when you see the cross section, is a very nice traditional breakout. If you visualize it like this, then this is looking down the well, up is north. And we could then see how the features were repeating in this well with the same angle. Very nice theory for the in situ stresses. And this was then up to 22 inches. And it was sometimes we see this a very traditional breakout, and then other places we have a more complex borehole shape that I've seen lately being modeled to with new theories where mud invasion is one of the driving mechanisms that cause hole degradation. And I think those theories will be very interesting to follow. It's not only pressure, it's more complex where mud invasion can be part of it, and then you have fractures and bedding direction. This is an example from a 16-inch section. We have drilling to the left, and then we have added on relogging to get the 4D component. And there is here a complex well shape where you have not only a breakout happening as you saw earlier, but you get a very interesting symmetric shape. And we have seen this in 8.5 inch, 12.25, 16-inch, 17.5 inch, lots of boreholes, and typically happening in shale. And this is likely related to invasion from the theories I've heard, but I don't think they are completely settled. They'll probably be developed more. So over to the electrical imaging with to look at bedding and fractures. So what I showed you earlier was the time of flight. This is then the amplitude part that we have processed, and you can here see a transition from high resistivity to low resistivity. And to the right, you see that you just touched the shale below, and then going upwards in the formation, and then downwards, and then entering the shale again. And this is from a 12.25 inch section, and there's not done any enhancement on the logs. They're more or less raw from the processing. It's static images. And then back to the first speech about mud cake. And we often get the question, how deep can you see? And at least we can see the formation behind. So the mud cake is not making a conductive isolator, so we can see through whatever mud cake there is there. But it's one of the factors that are very interesting for us to understand more and explore to get to closer and closer to the real and the actual resistivity. Here we have a 12.25, we have bedding, and then there are some fractures, so I see it, possibly filled with calcite. We had losses in the same area, so it can also be that there were losses that went through these areas here. And this is another example where you had a smaller zone, and again losses observed and drilling through it. These images are not processed compensated for standoff, but I think it's interesting to see that pulse echo radar is not highly affected by centralization. So as saw in the first image with the spirals, we were suffering here from lots of spirals, variable standoff constantly, but we can still see the feature all the way around. We are doing standoff compensation, which we are planning to publish later on, but we have got first results which are very positive. But even without standoff compensation, we can follow the features the way around. Some more examples where we go from increasing the angle on the valve here, 55 degrees, going to 54 This is 17.5-inch borehole where we have images all the way around. You can see in the middle that the tool is absolutely on low side. We had a 14-inch stabilization here in the 17.5-inch borehole. But still we can see the features. If you compensate for this, it looks much nicer. But in practice, those that are used the images will anyway see the bedding and the fractures. And here you see at 12.25, we're drilling more or less parallel to the bedding. This is an example where we have the caliper image in the middle. We have the electrical image to the left. And from the caliper image, you can see the spile, both those 90 centimeter and the 7 to 9 meter long spiles. And then that has an effect on the electrical image, but you can still see through it. Some conductive or low resistivity layers, and then some fractures that are more conductive, higher resistivity. And same here, you see a transition from a shale to chalk, if I'm not wrong, and still lots of spiles here. So that's some examples on the new tool that we have for pulse echo electromagnetic with oil-based mud. So if you have any comments or questions, we love to discuss these things.
I do believe Bernd has a question.
So first a comment. I'm seriously impressed. Very, very, very nice. Beautiful images in tough conditions. One question and one comment. The comment, I don't know, but this shape you were showing, for me it looked like lamination slip in a square. You could produce a square hole. I've seen this quite often. And you say it happens in shale, and it depends, of course, what your bedding is relative, what the shale bedding is relative to the borehole deviation at this point.
Yeah.
You said the inclination is 55 degrees. If you have a dip, an apparent dip to the shale around maybe 10, 20 degrees, we have seen this very often, for example, in the Draupner formation. When you go through and drill there, you get a squared hole like the one on the right, which is a little bit squared. That usually is lamination slip or shale instability, and you can model that very well. So it's a beautiful proof of what you can model.
Yeah.
The other one was the question regarding how do you record the images in vertical holes versus horizontal holes? Do you have top of hole and north, or do you have a relative bearing or a marker on the tool, which is the start of the...
So we use in vertical boreholes, we use magnetic, so we can put them grid north, for example. When we have more than 2 degrees, we typically use high side, so we use the accelerometers to orient it to high side, so then it's displayed to high side. We can also do imaging inside casing. So then we would use a sensor fusion of gyro accelerometers and also possible magnetometers to orient the images inside casing.
But it's preset. It's not some kind of magic auto switching if the deviation goes over 4 degrees or something. Okay.
No. It records all the data are recorded, and then you can choose afterwards which if it's 2 degrees or 3 degrees, you won't have the switch off point.
Okay, super. Thank you.
Yeah.
Thank you, Bernd. Jan, would you want to turn your camera on and ask your question?
I think there was some other that had.
Okay, yeah, sorry, I'm working in the office, not no camera. Okay, anyway, so I have several questions actually. Sorry, and if I'm not confusing, look like based on this new tool, you can provide 2 types of the image, right? First is called a caliper image. The second called the electrical image.
Yes. So
when you say identify the fracture, some stuff, you based on the electrical image, not the caliper image, right?
Yes, so the records the full waveforms So based on the waveforms, we can process that into a caliper image, but we can also process it into a microelectrical image or resistivity image if you want.
Yeah, what is the resolution for the electrical image?
Yeah, so
vertically and horizontally.
Yeah. The vertical resolution that we are looked at is 1 inch.
1 inch.
Yeah, from field data.
For the electrical image, right?
Yeah.
And for the what is the resolution for the horizontally?
Yeah, on the radiuses, when we have looked at the images, we see around ±1 millimeter.
1 millimeter. Oh, good,
yeah,
good.
but of course there are different conditions, so then it can be hard to verify this. But we have one publication for SB where we have looked at casing imaging, for example, and compared that with wireline calipers, and then inside the same axis.
Yeah. What is the formation formation retrieve range for the tool resolution? What is the maximum and the minimum formation retrievability limitation?
Yeah. So there's no clear answer to that, but it will be also it will be connected to the resistivity you have in the mud. So in different cases, you will have a different range and also accuracy. It will be dependent on the mud resistivity and the borehole size. So we started doing this a year ago to process the microelectrical images, and the tool is not fully characterized when it comes to the accuracy in resistivity. So at the moment we process a relative difference, but we will get more and more into actual resistivity measurements.
Okay, great. Sorry, last question. Did you calibrate your caliper image with another measurement, for example, like you mentioned with Roland? Maybe very difficult for the Roland because maybe the logging time is different, right? The Roland after drilling and your tool is during the drilling. But however, you have any way to calibrate with sonic or another different caliper measurement because the electrical caliper is totally new stuff and quite interesting.
Yeah, so we typically calibrate inside casing for every run, and then we have lab calibration that we have done, and we also look at the repeatability when we do relogging of information. That is also an indicator of accuracy and drift, etc. And then we have lots of compensation for temperature effects, etc. That we do when you run the tool. But in LWD world, it's always this challenge: what should you calibrate against? What is the golden standard for downhole measurements?
Okay. Yeah. Great. Thank you. Yeah.
Thank you. So we have two more questions. Oh, one. Bastian put his hand down. Udit, would you like to go quickly, please? Hopefully. It's
thanks. This is Udit Guru here. Excellent presentation. I just have one single question. All these images which you just showed in, whether real-time images or whether processed images after the logging, and if it is so, what sort of differences do we see both in real-time and processed images?
Yeah, so all the data here is memory only. We don't have any real-time telemetry at the moment. Working on it, but not there. After we have access to the tool after a run, we have 5 hours to get the first processing. So that's the typical deliverables for field logs.
Okay, thank you so much.
Right, thank you. We'll close questions on this paper. Thank you very much, Lars, for your presentation here.